And today's speaker is Professor Youngjae Moon, and he's a professor in the Department of Astronomy and Space Science at Kyunghee University in South Korea. And his background is in solar physics, and he also leads the Sun and Space Weather Laboratory there, where they focus on research on solar activity and sun-Earth connections. And I think his recent focus has been a lot on AI and machine learning for solar and physics and space weather. And so he is visiting Boulder this week and kindly offered to give a colloquium here at HAO. I will turn it over to you, and please go ahead.
Okay, many thanks for the kind introduction. This is Youngjae Moon. I'm so great, in great honor to give this talk. I made a little bit quite ambitious title. What kind of problems in solar physics and space weather are well solved by deep learning? But I confess that this question is limited to the practical experience. So I think it's also the Robert Jarolim is a very big guy, as in my understanding in this field. So you have a very great opportunity to talk about the future of the AI application to solar physics and space weather. So we have this group. Our group is the Sun and Space Weather Lab. We have some around 12 or more than 12, 13 the PhD and master student, and we have several postdocs. And we are collaborating with some computer science and engineering department. And also we are collaborating with the industry people in deep learning application. Actually, we started this work in 2016. It's the last 10 years. We have published around more than 30 papers, mostly in solar physics and space weather application. So from this experience, today I'm going to summarize some lessons and implication of our studies. This is a quick summary of what kind of problems in solar physics and space weather are well solved by deep learning. By the way, 25 years ago, I was a postdoc at Big Bear. At that time, I met Katie. we are collaborating about the same project. And also, at the time, I was visiting this HAO. I gave a talk about the solar eruptions. So 20 years back, time so flies. So now I'm here. So this is a little bit different topic, but it's nowadays everybody is talking about AI, right? AI is applied to so many different fields, even in science. So today I'm talking about the image translation area and improvement of empirical model and inversion problem and image super resolution and pixel to pixel translation and reduction of simulation time and 2D to 3D conversion and the space weather forecasting. Okay, image translation. Actually, I saw this paper 2016. So this is the image translation using conditional GAN algorithm. Actually, I do not talk about some details of deep learning algorithm for today. If you have any question to email me, then we are trying to answer. So I'm trying to talking about some concept and some application. This one is the satellite image, and this is map. Usually mostly automatically or semi-automatically they did, but we have a lot of data, right? So using the data, they made this algorithm. This is two network system. One is the generator, the other one is discriminator. Generator is trying to make the closest one. In discriminator is trying to make a real-like one. So both systems are competing and collaborating, and then make a real-like and the closest data. So at the time, I thought we are trying to how about trying to apply this concept to the scientific data? So is that I target the stereo A data. As you know, the stereo A data is mostly EUV data and coronagraph, but no magnetogram. Magnetogram is quite essential. So we are trying to convert from EUV data to the magnetogram data. Our initial result was published in Nature Astronomy. So this is the very initial result. So we show the possibility to translate from EUV data to the magnetogram data. So we continuously improved this methodology. The initial data is the very simple concept of pix-to-pix, but the version 3, we use the pix-to-pix CC, the correlation coefficient is introduced because your scientists usually using the, so this CC loss is included, and EUV data set and front side reference data set is mostly 1 week ago data. Then we can solve the problem of ambiguity of polarity. It's most difficult things is how to determine the polarity. But using this concept is usually we can improve a lot to pixel to correlations. And this one, recently we published the version 4. So input data is similar, but in this case, we consider the solar flux transport model there. And the output data is better. So we greatly improve. So at the time of near inferior conjunction, so we have the data, right? From the SDO HMI data. It's using stereo A data, we can make the solar radial vector data. This is one of the major results. It's the left side, SDO HMI magnetic field data. It's kind of ground truth. It's the right data, AI generated one, stereo EUVI data. If you see, closely compare, it's quite similar. And distribution is quite similar. And also polarity is not perfectly same, but quite similar. So I think it's the data quality is quite successful, I think. And the polarity determination also quite successful. So we can apply this concept to the stereo, and even we have a plan to apply the solar orbiter data. Do you have a question?
Those are amazingly similar.
Yeah, amazing, right?
Really impressed. Can you blink those? Blink them, that is, put them in a movie where you blink.
What?
Go between like one image, next image. Maybe not real time.
Not real time. Yeah, it's something different time, little bit
Maybe
different. Later, yeah. Yes, sir. Okay, we'll think about it. Okay.
Can I
Thank
ask
you.
a good
Yeah,
question?
sure.
Is this stereo data from like the recent flyby? Because like at the beginning, like there's always a separation angle between like the magnetograms, right? From
Yeah. Actually, we have get the data from the one synoptic period before. So we make the
I see. So it's
surface flux transport model
okay.
combined. Yeah, the surface flux transport model is very helpful to determine the polarity. Yeah. Okay, so even the variation of solar flux is very consistently moving, right? And also the even total unsigned current helicity variation is quite successful, which means if we have some enough satellite data, then we can monitor the long-term evolution of solar active regions. That's one big advantage of this kind of the AI applications. It's usually you are using the conventional synoptic map. but conventional synoptic map is not based on real-time data. So synoptic data. So some is 1 week ago, some data was 2 weeks ago, like. So if we have stereo A and stereo B, but not open, it's very limited, that one also. But if you have those data, then we can make a mostly, not all, but synchronic data set. So this one is the kind of a comparison between the AI synchronic map and the synoptic data in view of new emerging solar active region, in view of the newly forming the corona holes. Our data is much more consistent with the observations. Yeah, this is the very historic application. It's the Galileo sunspot drawings, mostly 400 years back. So we applied the sunspot drawing data, and then we make the solar EUV and even magnetogram data. And this one is the application to calcium 2K observation. Calcium 2K observation is quite a long time. It's as I know, is the 1907 or something. So that is the one application. So if you compare AI generated data and SDO HMI magnetogram, this is the ground truth. Our generation is quite consistent with the ground truth. This one is the application to the helium 1083 nanometer data. It's probably this one made by HAO, SN. No?
NSN.
Yeah. So it's using SDO 2 wavelengths data. We are making the helium 1. If you make from the satellite data, so we can get some continuous data set. That is another advantage. And period of the data bank, data break. That is the another types of advantage. Yeah, this one is also the K-core. K-core is probably HAO data, as I know. All right. So, helmet streamer is very well reconstructed. This is the target data. Is the down is AI generated K-core. AI generated K-core is quite consistent with the target data, and even the small scale eruption. And this one is the application of denoising. We solved this denoising problem using the single frame input data, 21 frame integrated data. That is target. So if this one is the target, and this is the denoise, this is the difference map. It's quite well. I think our denoising is quite successful. This is the second topic. Second topic is improvement of empirical model by deep learning. We applied the IRI tag map. The IRI tag map is quite popular, the empirical model in ionosphere, but is some the low latitude anomaly data is not represented. So we made some of the pair data. So we make a deep IRI model. That is new model. It's based on deep learning. So correlation coefficient our model with IGS tag data is much greatly improved, and RMSE error also is greatly improved. So this one is the difference map. Difference map is the mostly well catched, so the equatorial anomaly enhancement. This one is moving. This one is very recent, 2026, this year. Improvement of IRI 2020 electron density profile with cosmic radio occultation data. So this is very simple model using the multi-layer perceptron. If you compare, it's more consistently the improvement of empirical model by deep learning. Okay, the third one is the inversion problem. As you know, it's mathematically is the inversion is kind of ill-posed problem. It's not easy. It's TEC, total electron content, is the kind of integral of electron number density for given height, and it's an integral of the line of sight. So we are observing the mostly integral quantity, but we have some IRI, the empirical data set, that is the fully three-dimensional data. So using the three-dimensional data, we have trained a model of two inverts to derive the vertical electron number density profiles. This one is the result. We have compared our 3D inversion data with IRI and also incoherent scattering radar data. So our model data much more consistent with the incoherent scattering radar data. As I know, the incoherent scattering radar data is one of the most accurate data, as I know. So even RMS error is much better in different latitude data. This is the near equator and middle latitude and even high latitude data. This one is the RMS error also, especially in the nighttime, is the error, RMS error is greatly reduced. This the next topic is the image super resolution, and this one is the original STO-HMI data. Is the STO-HMI is the degraded, and the AI generated magnetogram. Is the AI generated magnetogram is much more consistent with the original data than simple bicubic or other data, and also we apply this concept to the Hinode data. So that is shows a possibility to have a high resolution magnetogram data. But this one is a very interesting application, and we have some plan to extend this application. This one is a pixel-to-pixel translation. It's mostly we are thinking that the one image is one data. So in this application, our intensity is a kind of integral of DEM of along the line of sight. So we are using every pixel data. So we applied the AI application to derive DEM distribution. So we found very interesting result here. This one is the DEM distribution of the corona hole area. So this one, the single frame data. Is the red one is single frame, and green one is the step or 50 frame integration data to reduce the signal, to improve the signal to noise ratios. And the blue is our fully connected network data. So our data is much closer than the 50 frame data. Even greater than usually log T is 66 now. It's like it seems to be contaminated by the stray light. That is our speculation. So usually one advantage of this kind of pixel to pixel translation reduces the random noises. So to give a better result of DEM. That is one interesting result. So we have a plan to extend this work. The next topic is a reduction of simulation time. There are so many numerical simulation model in the sun and in the heliosphere. This one is the one application. We are using the mass data, the very popular, the heliospheric data. So this one is the input boundary condition, and this is the simulation data. It depends on computer, but it's mostly several days, or probably supercomputer, maybe several hours. I'm not quite sure about this the time, but our deep learning model is just 45 seconds. Not exactly the same, but quite similar. So if you want the near real-time simulation data set, I think it's the deep learning application is quite promising. This one is the reduction of simulation time using the physics-informed neural operator. It's the input is the 2D photospheric vector magnetic field. So it's a thoroughly used some pin, right? Some little bit different, but we are using the physics-informed neural operator. So you are considering data loss and the physics loss. So, our method is the conventional method, at least several hours, but our method is just 1 second. We can get some similar results. So our model can estimate 3D free magnetic energy in real time. That's the advantage of our research. This is the ongoing and preliminary, but very important one. So it's 2D to 3D conversion. So estimate the CME 3D parameters using deep learning from single view and even the multi-view observations. Now these models are performed manually, but user-dependent, take a long time to execute. So we are testing. Can we determine the three-dimensional parameters from CME images using the deep learning method? So this is the input. This is the output 3D parameter set, radial height, angular width, the latitude and longitude. So it's the first step is you are using the synthetic image. It's a simple binary image like. So you are very popular ResNet like the CNN algorithm. So we derived the angular width and latitude and longitude and radial height. So this is the preliminary result. Yeah, still we have still we have RMS error. Not so big, but I think it's still we have things to do. So this one is the real observation data. So we making the manually this kind of the binary data from data. But is that this is mostly very big HALO CME. So we have some ambiguity of the radial height and angular width. Very interesting things. This one is the full ice cream cone model application. But we applied two kind of models of deep learning. So we have different results. So I think it's still things to do. But I think it's if you have some little bit asymmetric data, it's relatively successful. But in the case of symmetric HALO CME, it's quite difficult to do. Okay, Katie.
Question. On your previous slide, what was the training, what was the training set? It was simulated CME?
Yeah, simulated CME.
Okay.
So we have a lot of different position. We have a lot of different angles and then make a huge data set.
Okay.
Yeah.
From a simple.
Yeah. Simple geometry.
Okay.
Yeah. Yeah. Okay, this is for space weather forecasting. We did a lot of space weather forecasting. I'm summarizing the key results. This one is the current IDS tank map as an input, and model is the conditional gain, and also output is a predicted global tank map for the next day. Very simple one. So our simple model is better than code. The lately is we have made them better version. This one is the application to the solar flux transport. That is mostly empirical model. The empirical model can be well done by deep learning. So this is the conventional solar flux transport model, and that is target data. This is our data. Our data is the well constructed of the background field, and also we have tested our model using the synthetic images, synthetic data of simple bipole configurations, and then the AI generated data, and then we can successfully reproduced the differential rotation and meridional flow. So even some aspect is better than the conventional method. And another one is the rim flare model. It's the rim flare model is very difficult because of projection effect. It's the magnetogram data, white light images have a significant projection effect. So relatively less projection effect of EUV data because of optically thin. So if we are using the total intensity of EUV data and the rim intensity data, we are making a simple empirical model and multi-layer perceptual model, and we have compared with the existing NASA CCMC player scoreboard data. Our model is much better than. And nowadays, we are doing some new method of symbolic regression. It's kind of a little bit general version of simple regression. It's a simple regression is like linear or quadratic fit or simple ad hoc assumption of functions, right? Yeah, but you are doing some no specific assumption, only data-driven model. So this is the simple example. It's deep learning training from vector magnetograms, and then you are trying to predict the ghost player, a major player. So from the vector magnetogram, we can get the feature traction and feature selection. And from target data, we are making the probability of player. Then in Y can be expressed as a function of X. So we are trying to derive some specific function without any assumption. So we are using the most popular, well-proven model is PySR. This is the one interesting and preliminary result. Our result is here is the three parameter. It's the R and H, current helicity total, and also the absolute current helicity. These the three major parameters are important in player forecasting. That's our result. So we estimated the total variance in the predicted probability. So we found that is the ATC total times ATC absolute is the major part of total variance. So this result implicate that high R value is a necessary baseline for player occurrence. The Schreiber already mentioned about this one. And additional important one for player forecast, the total current helicity and net current helicity. So this is the new finding. We have recently submitted this paper. And this one is the 3-day forecasting of solar wind speed with multimodal input. So input is the STO AI image and additionally solar wind speed and the simple NLP, and in addition to the inception block, and we successfully predict the solar wind speed. And our result is well reproduced, right? The solar wind speed enhancement, and our model is much better than at least our comparison. Much better than Wang Shili Anil and European space wind solar wind empirical model. It's even better than the persistent model. And if you see in 2016 and 2017, our correlation is mostly better than 0.8. So our model is well reproduced the solar speed variation in the case of solar wind speed. This one is the more comparison. This is our deep learning model. And actually the Space Weather Prediction Center asked this comparison. So it's this Thursday, this coming Thursday, we are supposed to give a talk. It's the several months ago, I did a talk, but they asked some more verification. So it's this, we did this kind of things. It's it's based on CCMC data, the SWPC data, European solar wind data, and even persistence. One impressive thing is recently we developed a very simple empirical solar wind equation, like model. Actually, that is model, but solar wind model. So it's deep learning model is best, but symbolic regression model is very close to one. We are trying to understand this one. That is very interesting. This is the solar wind speed. We have 3 components here. The first one is the area. The second one is contrast of corona hole. The last one is the persistence of 27 days. So 3 components. Only European model, they consider the area itself. But we have found 2 additional parameters. We combined using the specific form of equations. So this square root means mostly harmonic mean. So we are approaching the more data-driven the equation. Data-driven equation is more interpretable. So that I think the symbolic regression is one of a promising approach to get between the deep learning model and the so just a simple empirical approach.
There was a question
Sure.
online.
Online? Okay.
Yeah, thanks.
Please go.
Yeah.
ahead.
So I was wondering what's the distribution of the training, validation, or test as you are showing the period of 2012 to 20. So how much the sample is from training and test?
Okay, so can you answer?
This table just example, but in the I not so
This one is a much more samples indeed, right? Yeah, I think we have trained probably from January to August. That is training, right?
oh, yeah,
Yeah, and the validation is the September, and the last month is we are for testing. So every year is included to take into account the solar cycle effect.
Okay.
Okay.
So you are training for whole year and only predicting the last month.
Yeah. We have trained 8 months for training and 3 months for testing. Every year.
For every year?
Yeah, 2012 to 2020.
Okay, thanks.
Okay. Yeah. Okay. It's one of the challenging prediction in space weather. I think it's the IMPPG. It's probably, we have tried several different ways, but mostly we failed. So we have changed our strategy. Not all cases, only some significant cases. Only we have considered significant southward components. It's most of the time is near background, right? So because of that, it is very hard to predict. So because of that, we have only considered this the next 6 hours. It's not bad, right? I believe that not bad. That was published in APJ supplement last year. So I think that is very successful. That is okay.
Question,
Sure.
you mentioned that you tried many methods
Yeah.
that failed.
Not method, but important one is the data set.
Okay, I was gonna say, did you publish?
No.
No,
No.
I think it's important to tell people
Oh,
or
okay.
tell the community
Oh, okay.
research that, I mean, it's still research
Yeah, right.
and outcome,
Yeah.
you know?
Oh,
And so if you have, so then you can learn you know, what did work, what did
Oh.
not work, and we can understand why. I think that's important.
Yeah, thank you.
Please.
Yeah, yeah. Okay, this is the continuous the forecast. So our model is much better than simple multi-layer perceptron or regression method. Okay, this one is the many people are GPT talking about GPT or Gemini or some Claude recently co-work or some too fascinating, but it is very hard to follow, right? Yeah, that's true, I think. So we started this work is the space weather assistant with GPT. That is very simple model, not new things, but we want to include some simple chain of thoughts and retrieve tools. So using the immediate analysis assistant and external sources, text-based data and image-based data. So we want to help some operator, the Korean Space Weather Prediction Center. They are interested in this kind of things. So we are developing this one. So recently we are upgrading using the multi-agent system. This is the supervisor. It's the R agent, S agent, D agent, and we include more external sources. And also, we are implementing some local models. So more comprehensive analysis and also comprehensive forecast. So this one is some Gemini Pro, Gemini 3 Pro R agents. So not bad. This until now is relatively good one. So we have some external sources, and also we are including our local models, beam player forecast and ensemble empirical models. Okay. Recently, I joined the L4 mission. The L4 mission scientist is I published one paper about the scientific perspective of L4 mission. It's the L5 Vigil, the Vigil mission. So it's the Korean government is considering, not determined, but considering the L4 mission. I was the group of scientists to have a feasibility study. So because of that, I'm interested in some onboard AI. It's that we have two kind of burdens about that one. The main burden, is the SDO AI data. Is telemetry is the 130 megabps, and the another geosynchronous orbit in the Korean satellite. There is the more than 100 megabps, but in the Vigil, it's the only 1 megabps. So there is very serious telemetry problems. We want to get very serious, significant the magnetogram data, UV data, and the coronagraph data. But it is very hard to get. It's solar orbiter. We have the similar problems. So we have to solve that one. It's a two kind of approaches. One is onboard AI. So some data compression based on onboard AI. The another approach is like kind of using deep space optical communication. As you know, the Psyche mission in JPL is proved, the possibility. It's probably 3.2 AU. It's quite a long distance. This is the very preliminary result. It's under revision in APJ. So we applied several different compression. This one is LICE or JPEG. There is the conventional compression method. So we are using the pre-trained AI and fine-tuned AI model. So this is the DEM determination based on in compressed data. So our model is much more constant with the original data. And additionally, this is data compression rate. Data compression rate is around 20 times compared to the original data, which means 20 times saving. And so that is one, great directions to relieve the burden of telemetry in deep space mission. So this one is the ST. This is the metric data as a function of bit rate. So our AI model is much better than the conventional method. So we are trying to test more in the AI chips using in ground-based AI chips, and we have a plan to test in the space mission as well. Okay, this is the final slide. Actually, probably in less than 10 years our group is making the several different deep learning model. It's the numerical model. It has a quite a long runtime, right? It's several hours, even several days. So it is very hard to combine some several different components, right? So you are learning, but one of the big advantages of deep learning model is the inference time is quite short, just a second or just less than a minute. So we are making several different models, and we have a plan to make some integrated space weather forecasting is by deep learning. So that is our major directions. So thank you so much for your attention. Yeah. Any question or comment? Yeah, sure.
This is very far back in your talk, so you do not have to find the slide if you don't want to. I know the paper is out, but I don't remember the details. For the far side where you're conditioning on the EUV, how do you treat new emerging regions in terms of, especially in terms of flux, but orientation, like polarity insertion? How do you do that?
Oh, yeah.
Is it HAO law primarily?
No.
Okay.
Okay. I think that was the most difficult issue to solve for our group.
Okay.
It's many people ask that issue. Yeah, right? And I have that question. So we have a lot of different trials. It's finally, we believe that we mostly solved it.
Okay.
Yeah. So key point of the reference data set. The ambiguity polarity is not dramatically changed. Ambiguity background field.
Right.
So we can use some 1 week ago data, but now the latest version 4. So we are applying this data to surface flux transport application. Then even 90 degree and even the 180 degree, but the polarity is well conserved. So this polarity is used for determining the polarity. And how the new emerging flux region.
Yeah.
New emerging flux, so eventually result in some brightenings or loops of EUV side. So that is we don't know some detailed process.
Okay.
But anyway, quite successfully is the print version is doing well. That is this one. That is amazing, surprising to us, actually, even to us. So this one is the real ground truth data. This one AI generated one. That is our print conclusion.
what's the separation angle for those two observations? You were saying it's
Yeah, mostly, yeah, here. Is this Earth? SDO is here. Still, it's the most the same.
I see, I see. Mhm, mhm. Okay. Yeah.
So we have a plan to the solar orbiter data. It's a solar orbiter data has a near real-time data, it's final data, and EUV data. So we are trying to make a magnetogram data using EUV data, and then we want to compare with the 3 magnetic fields. So we want to show some the feasibility, show the feasibility of the far side magnetograms to our community.
You had a question.
Yeah, sure.
Jeez.
All right, can you
Oh,
go to the speed up simulation, the global MHD
yeah.
model?
Yeah.
So what is that density image? The outer radius. What is the radius at which you plotted that? Yeah. Here. Oh, you passed it.
Okay, sorry.
Yeah.
Yes.
So what is the outer radius of this model?
Radius.
Density at what radius?
Oh, yeah. Yes.
So
I'm sending the information of the paper. Then I think more detailed information. I'm sorry, but it is 6.1713 radius.
okay. So
Yeah.
so you get both. So you reach a steady state much faster. You're saying
Yeah. Much faster.
In
That is a
45
big advantage.
instead of a few days. Okay.
Yeah.
So you get both. You not only get density, but you also get the magnetic field and
Sure. So we derived several different parameters. Yeah, right. The density and magnetic field, and what else? Even velocity. I'm not quite sure.
so everything you basically get the model steady state solution in
Yeah.
5 seconds.
Yeah.
And give the input of the magnetogram. That's it.
Yeah. That's it.
Okay. Thank you.
Thank you.
I think there was another question online. Kevin?
Yes. Hi. Thank you.
Hi.
Interesting talk. A lot
Yeah.
of stuff. A question about the compression that you were
Yeah,
showing.
compression.
Um,
3 points.
so what additional information or values are being taken out by the higher compression? If you were to look at what the difference is between the AI-based compression and the RICE or JPEG, is it taking out more noise? Is it taking out some structure that's not important?
Yeah. Probably structure and data distribution.
Mhm.
So can you answer? Or anybody?
Mhm.
Okay. As I know, is we are using the variational autoencoder, as I know. Yeah, it's
Yeah.
it's
Okay.
probably, yeah, I cannot answer directly, but we can guess. So
Okay.
we can guess.
Mhm.
So the
Yeah.
data distribution is well trained. So
Right.
they are trying to convert the more quantized data. It's like
Mhm.
they are using the A-bit data, but keep the contrast. That is my understanding.
Mhm. And is that tailored to a specific analysis method? I mean, is that optimized for the DEM, deriving a DEM, or is it
So we didn't
independent
try
of the?
to optimize the DEM. We just use the 2 different way pre-trained AI model. This is not just computer science people developed model, but this one is a little bit optimized, but not improved. It's mostly the same. I think it's in most of cases, they already well trained computer science people, well trained this model. So, it's not specifically DEM optimized, not specifically the solar side
I see.
without the optimization.
Okay, that's good. Okay, great.
Thank you.
Thank you.
Matthias, I think you were first.
You mentioned super resolution as one of the applications.
Yeah.
But it was only one slide. You went very quickly through it. So I
Yeah.
just wanted to understand a little bit better what you're doing there. Is this just a more fancy way of doing a deconvolution of the data, or do you actually get resolution higher than the essentially what the telescope, the diffraction limit of the telescope? I mean, how far do you push this here?
It's a, in the future we can do. I think it's a more comparison with conventional, but we didn't do it here.
So is this essentially just something like you deconvolve and then you take the PSF of the telescope out to get higher resolution, or what? I mean,
Is it trained only on the HMI original so that you're
Oh,
generating?
it's the, yeah. It's the,
And your degraded is.
degraded.
okay.
It's the,
Is it how is it degraded? Is it just a Gaussian?
Gaussian convolution and,
Moving.
Then it's just a deconvolution essentially you do here, the machine learning approach.
Yeah, deconvolution. Yeah, right.
I think Nan had a question online.
Yeah, I'm sorry if I didn't understand what you've done, but if I understand you look at solar images and you project forward how those will evolve. Have you looked for an entire solar rotation and see if what you project has really emerges as the sun rotates?
You mean the far side magnetograms? You mean?
Yeah,
Right.
you've done for the far side. Have you looked for a complete solar rotation, for example, and does your projection really come true?
Yeah. This one is mostly one solar rotations. So with the
Yeah, you've done it
in
for
character
stereo. Have you
longitude.
looked for even longer projection times? How successful the model is?
Yeah, actually we did some statistically the comparison. And this one is, if you see our recent paper, the APJ and yeah.
Yeah, I'm
This
sorry,
is
you've covered a lot of material in a
the
short
latest
time.
version. So we have compared with statistically is the R, zeta, and pi, and the test data set.
Okay.
And this one is the evolution. The different times. So
Okay.
this one is the quite a long-term evolution, right? 2011, October to December, right?
So 3
October to
months.
December. Yeah,
Okay.
and we can monitor consistently the evolution of active region in view of the magnetic flux, in view of total unsigned current helicity.
I see. Okay, thank you.
Okay, thank you.
Going back to Matthias's question about super resolution, when you apply a smear to HMI data, you get rid of a lot of noise. And so the question I want to ask is, what would be the result of your recovering super resolution? Put the noise back somehow, get what it was, or
right.
Put it back before you ran, or maybe you're already doing this. I don't know. But if you put the noise back before you applied the reconstruction.
I think it's already, he mentioned this kind of deconvolution. Suppose we have the target data. That's the one difference. We have a ground truth target data. So we can train the simulated degraded data to find the original ground truth. It will be trained. So that is one advantage. I think also the magnetogram data have some self-similarity in small scale and large scale. So I think we applied this one to the Hinode, and then we compared with the better better result with in the comparison. So I think that is the one of the possibility to work more. Okay, thank you.
I think it would be very interesting, you know, the work we've done with Super Cynthia
Ah.
and Super Cynthia LOS.
Mhm.
And I think, which is another version of making high resolution and also vector from via line of sight. I think we should do a quantitative comparison.
Yeah,
It could be very interesting.
yeah. It's the last week I visited the New Jersey Institute of Technology. They are doing the similar works. So they are using the from the data. So they are trying to gist the GST data and even DKIST data. So that's another part of very fine scale structure of magnetic field configuration. So that's a very interesting part of the future work.
And maybe I have a follow-up question here. I mean, well, I'm always a little bit confused with the super resolution. I know that some people push it much further, but they kind of take HMI data and kind of create something which looks like Hinode.
That's Super Cynthia, yeah.
Yeah, but what do you do with this data then scientifically?
Scientifically, we'd like to forget people to use it for data driving, for example, but also just to one of the large things is that towards the limb, I'm going to be very careful here. The pipeline data from HMI, meaning not the best you could get from HMI, but the pipeline output can start to have some problems that the Super Cynthia does not, that really has solved. So temporal stability, and also then, so it doesn't look like it's still on the HMI grid, but has been trained so that some of the issues that HMI has in terms of bias and overestimation in the noise, like basically the noise is very much decreased. So that's a big factor, but the temporal stability is quite good. So it's still on HMI grid, but it's just been trained to emulate HMI kinetic. So but scientific, I think is a good, what do you use this for? And I think one of it is, just is as you go away from dissenter, you're no longer at the native. I mean, people say, oh, I've got, 700 kilometers per pixel. It's like you don't anymore, right? It gets, so being able to get a better idea of what the underlying field is, even when the observations the pixels are effectively getting bigger as you go towards the limb, I think is making that more consistent is an interesting.
It's another part of, I think advantage is we may compare the high resolution data with some even simulation data. The simulation data is very fine, right? So magnetoconvection can be compared with some observation, and also the super resolution data. That's the one direction, I think.
Yeah, I mean, the one reason I'm asking this question is I always kind of get the feeling almost that when you go to the super resolution, at some point you start making up information which wasn't there, and then you have to be careful what you do with it.
Yeah, sure.
You also have to be careful because everything's coming from polarized light, right? And the telescope, if you're going from different apertures, will do a signal mixing that it's not going to be handled by all of this. So, and the inversion algorithms and that. So, there is a lot of being careful. I think,
Yeah, sure.
in terms of the details. That's very for sure.
Yeah, we agree. Yeah.
Any other questions?
Oh, yeah.
I'm interested in the CME parameter estimation
Yeah.
you were showing. Can you give maybe I missed it. Can you give us some more details about how it was trained in terms of simulation data and how the evaluation?
Yeah. Oh, okay. We have one model. It's kind of a simple geometry, full ice cream cone model. It's like N and then covered like a semicircle like. And then you can make a parameter. And then we can construct with different position, different latitude, different longitude, different radius, and different angular width. So, and we can make a lot of images, right? Synthetic images. And then we know the ground truth of the whole parameters. And then we can reconstruct the, project the image. In only project the image, we are trying to derive this parameter. So this one,
And have you applied this also to observational data?
This is a very, this is one application. There is the very elongated to the some rim region. This is quite successful.
Mhm.
But in the case of very hollow like symmetry, then it's our even similar CNN model, but we have quite different result. That is our current limitations.
Okay.
So I think it's the, in the case of a very symmetric hollow CME, and so we have the ambiguity problems. It's a small angular width or large angular width. It's a very similar result of hollow-like CMEs. So because of that, so that is a very internal problem. But if we are doing the similar simulation with the multiple observation, like the Lascaux coronagraph and L5 or L4, then that's successful.
Okay.
So you want to demonstrate the importance of multiple observation. That is one part of the directions.
Okay, thank you.
Thank you. Okay, thank you so much for your,
Thank you.
thank you.